It is our great pleasure to have Celie talking about Brownian motion and noncommutative geometry. Please.
Okay. Yeah. Thanks very much for the invitation. Yeah, I'll try to explain something that I'm recently thinking about the connections, relationships between this stochastic process and the noncommutative geometry. I hope it's going to be fun. I try to work with my students like Chang Wang and Yang. But let me report something very general. Recall the construction of like the quantum product. Like say in Formal-Witten theory. It's a little actually related to the talk of Hero in the morning. Suppose I have like a Taylor manifold. On this Taylor manifold, we can do something like this. So we have the cohomology ring on this Taylor manifold. And this is a ring, so we can basically multiply elements together. So the classical product is like, suppose I have some elements like alpha 1 and etc. Alpha p. So I just take the wedge product. And this is the classical product. Now there's a way to do some kind of deformation correlation of this product, which is called using this quantum cohomology ring, the quantum product. And geometrically, it's something like this. Somehow you can get a product, but let me write this in such a way. Some kind of Q deformations. Some Q deformations. And the leading term is like the product. Some correction terms. The way you construct this product is by, for example, counting holomorphic maps of the sphere to the Taylor manifold. And what we're going to do is the following: like you put some mark point on the sphere, alpha 1 and alpha 2, etc., related to this insertion. And this insertion is some kind of local correlation or local observables you can insert into the story. And you count such holomorphic maps. And you represent each holomorphic class by some side source. And you can somehow deform this product by counting holomorphic maps, spheres, back to this Taylor manifold. Some information indicated by this mark point. So this is a very classical story, like quantum cohomology. Now I want to do something even simpler. Simpler model. It's a simpler quantum mechanical model. In a similar fashion, suppose I work on a classical phase space. Now, on this phase space, I can look at functions on this one. For example, I look at holomorphic, like polynomial functions. Okay, right, something like that. It's the coordinate on this phase space. Then this is a ring window. Like we can just multiply elements. So we have a product. Now we just multiply elements, like say F1, Fp. But it just multiply with P function. Yeah. But this is a very classical product and rather trivial. Now I will explain something like explain the quantum product in the same fashion. So I can basically deform product. It's like point-wise product. I can write something like this. So some kind of quantum product using this quantum mechanical model, and the leading term is something like that. This classical product plus some quantum correction terms. And I will try to explain how to construct such a map and some kind of properties of it. And the construction is very similar to this counting stuff. But we're going to work with something, a simpler geometry, like the circle. And here we were counting like holomorphic maps, and here we're just counting circles. And we're going to use this probability theory to arrive at this point. And this is how it's connected to the title. To understand how this works, let me first explain this some classical objects. First one is the Wiener space. So let's consider the following space, like continuous functions on this interval. So here, it's basically all continuous functions on this interval. And with a reference point, let's say gamma 0 tends to 0. I just say even dimensional space, and this is like a path space. Then on this path space, there's actually a very nice probability measure, mu, the unique probability measure. Which is called a Wiener measure, such that it's uniquely determined by the following property. For example, first you put some points on the interval. Some finite points. Let's say this is a P0, starting from 0, and there's some point here, P1, etc. Look at any kind of finite points. You take any kind of bounded measurable function. And this measure is basically uniquely determined by the following property. You try to integrate on this path space, this Wiener space. With respect to this measure, and you try to integrate something like this kind of function, interpolate this point or this function at some points. Say, evaluate this one at some time, gamma t1, gamma t2, etc. The value of these integrations has a precise answer given by equals integration in a finite dimensional integral and this property. Let me first write it down. And this function psi x1. Yeah. So here, h this factor is the heat current. on the line. The kernel. So if you require this property, like you insert any kind of a measurable function, and the value of this measure is given by this property, the particular answer, then you can show this one has a limit precisely giving rise to this this probability measure. It's called a Williams measure. And sometimes for like in probability theory, people write this one as like expectation value, this kind of property. And this allows us to do some nice integrations on the path space. I will try to explain how this is related to some kind of construction, reconstructions in this noncommutative geometry. But this is the thing. So with this measure, you can construct some interesting random variables, which is called a Brownian motion. And it's a more popular stochastic process in the following way. We can consider this random variable. Let's call this one map, this BT. It's a function, it's a map, it's a function on this path space, on this Banner space. By sending, for example, this gamma to like a BT gamma equals sigma gamma T. So sigma is some positive number. I try to explain this factor later. This is going to be playing a very important role. So this is a function, measurable function of this probability space. It is called it's a particular random variable having the following property. First, if you look at this increment in time, it has the independence property. So for example, if you look at the increment difference, this is the independent. For like previous process, for example, independent of the time when it's before if you want. And actually, it has a precise probability description. Here, there's a random variable here. It's a normal distribution. Centered at 0, and the variance is like sigma e2 minus e1. Usually, you just take the sigma to be 1. This is standard Brownian motion, and this particular realization of this Brownian motion is called a Brownian motion in canonical model. Of course, there are many other properties, but let me just say this particular thing we're going to study. And on this one, the next story related to this quantum product. I'm going to work with something on the loop space. I'll show you like how this product can be realized by doing something like a circle to the plate space, and you put some mark points. Like 1 and 2 essential, similar to this picture here, and do this kind of quantum intersection. So how to get this circle? Actually, there are different ways of constructing the process on the circle. I'm the simplest one to get this one, so to get this process is to use the so-called Brownian bridge. You can get this, for example, this CT. Look at the difference. You treat this function, let's say, because the Brownian motion starts from 0, and then when t goes to 1, it gets to 0 again. So if you think about this one as something on the circle, it's called a Brownian bridge. And the original Brownian motion here, if you look at the generic point, it's represented by something like this. So if you show the picture, you start from here, and then this is a very popular thing. You'll see any kind of stochastic process is something like that. It's like random walks, the limit of random walks, is like that. And then you look at this Brownian bridge, then it goes back to the original point, 0. So you view this one as something living on the circle. And then for our purpose, we need a little bit reduced version. Let's call this one PP bar. I want to subtract some constant mode of this Brownian bridge. Let's call this one reduced Brownian bridge. So if you look at pictures, it's like this one is like starting from here, and then you start to some random stuff and go back, and you subtract some constant modes, and you get this reduced Brownian bridge. And this is very standard constructions in probability theory. Okay, so that's going to be the basic framework building block we're going to play with to understand some parallel constructions of this guy. Let me show you how this works.
Bar does no longer start at 0, right?
Which one?
The CT bar does no longer start at 0.
It's not on 0, yes. It's okay. And now, let me show you how to construct such a quantum product from this probability. So first, I need to understand this correlation map. So let's call it one topological quantum product. Again, for simplicity, let's work with the classical phase space. Take R2n. Like now, let me choose the coordinate like for the positions and momentum. It's like x1, xn, p1, and pn. And then I look at functions on this one. Let's look at polynomial functions. For simplicity. Now I want to like basically deform functions here by some random process and look at some quantum fluctuations. And by the following stuff, like so, let's introduce 2n independent reduced Brownian bridge. So for each variable here, and make it run random in a way. So let's call this one x1, xit, git. And make it random. And then we try to write down this map, this correlation function in the following way. So let's define the topological quantum product. Just here. Let's use the same notation like the bracket. X1, XP, and essential, let's say M, XP. Suppose I have M functions on the phase space. I mentioned like classically, you can just multiply these functions together. Now, quantum mechanically, we want to make it random and look at this expectation value. And this is the definition. It's given by integration. So let me first write it down. So I insert M points on the circle. One in cyclic order. So this is one particular connected component of the configuration space of M points on the circle in cyclic order. Now I compute some expectation value of the following process. For each function here, I look at some quantum deformation by this fluctuations by this random process. So I look at it like x plus this fluctuation at T1, T plus this fluctuation at T1. So just deform the first function by this deformation. And essential T plus M.
Should it be xi or something like that?
Yeah, that should be I here. Let me be sloppy. Yeah, it should be I here. So I want to simplify it because it's going to be long, this formula. Yeah. And look at some particular weight by this integral. And there should be also I here. Let's take the sum of i's. So let me be simple, sloppy a little bit. And compare this expectation value and divide it by expectation of the weight. And you can see like this expression comes from like topological quantum mechanics. And then for this old process, like this is a reduced Brownian bridge with particular variance. And the important thing here is have to take the particular limit, the large variance limit. Take this large variance limit. If somehow this large variance limit is play the role of like some kind of large volume limit, then it goes to some topological limit. And that is the formula. Yep.
So you're now taking this Wiener measure for each variable x and for each variable p, and all of them have the same variance.
Yes, independent, yes. But copies of this stuff.
But that doesn't sort of correspond to some kind of maybe calorimetric, which corresponds to that symplectic form, right? Because you have your canonical symplectic form on R2N, and right now you need the metric for the Wiener measure, and that's the metric that you
Yeah, the measure comes from, yes. I take this limit to remove this dependence on the metric in a way. So this actually comes from AKFZ model from circle to the symplectic space. Yes.
No, but to define the Wiener measure, you first introduce the metric, and then you sort of take a limit where the it would disappear.
Yes.
Is it right?
It's a plot. So the output here is like this large variance limit. It is the precisely plays the role of like topological limit. That's the upshot.
Well, hold on, that's a very strange expectation value. So that's expectation value. I mean, what is that integral? Value dx.
This one?
Yeah.
Yeah, this is like this particular weight. There are many different ways to understand this this weight. One thing is like if you look at some AKZ model from the circle to some target, or you can write down this actual functional very in a natural way, and this also arises in the study.
Sure, but I mean, what is the dx? Are you doing an eta integral?
That's a great question. Yes. For this case, if you can generate it a little bit more, you can. This is the Ito integral, but this is a trivial part of Ito integral because these two stuff are independent. They're not mixed together in a way. So if you integrate something depending on x as well, just have to use Ito integral to define this term.
But it's weird, like the expectation value is itself like an eta integral. I mean, so you're doing a double, like a eta integral with the eta integral inside.
Yeah, let me say it this way. You can insert something more if you integrate things like that. Some functions like say x and p and dx. And this has to be equal to. Yes. But this case is a little bit trivial. I mean, these two stuff are completely independent. So you don't have the non-trivial part of Ito integral, but it is a Ito integral, yes. So for in a general way of saying this, like you can integrate all the integrals here appearing as an Ito integral. But in this case, the Ito integral here is trivial. Not that trivial, but this you don't have the most non-trivial part of the Ito integral. This Brownian effect. But if you try to integrate something like that, you will see the effect of Ito integral. Because it's Brownian and the square is going to be dt, something like that.
So this exponential term at the end of the day, that sort of depends on which Brownian path you had, right? Which element you have in your Brownian space. And then you use it as a weight for this functional, and then you're taking the expectation value with respect to the Brownian, the beta.
Exactly. This is the expectation value with respect to the beta measure. Yes.
In that sense, it's not like a double.
Yeah, then that's an ordinary integral, like the expectation value on the outside is the integral that you're doing. So in that PDX, it should, so you're integrating over all paths, right? So once you pick the path, then you're just doing an ordinary integral over that path. It's a normal DX in a way.
In this case, it is. I mean, but just because it's two, just they're independent as well. Yeah. I mean, like if you can insert much more interesting, more complicated functions, then like say you integrate something like OX, and then you need to say integrate the real part of the integral. Yes. But this way is rather simple. So you can the ordinary integral and the integral is the same. But if you want to insert something more complicated, you need to now that's the definition for this quantum product. Now let me show you how this is related to this non-commutative geometry. There are several ways you can play with this random process, and well, let me try to explain something very basic. It is social homology.
Maybe before you go on, so what are the properties of this product? I mean,
I will show you up to.
so that's gonna.
It's gonna be related to.
Okay.
It's you will see this one after I explain this social homology.
See, how about for the ambiguity there, like if f has like, I don't know, x times p, so
P dx. It's on a circle, it's a periodic boundary condition, so you don't see the point. And as I mentioned, like if you if you want to integrate something like that, you will have this problem, like apply x. If you do a non-trivial integral, you have more complicated situation. I haven't studied much about this case, but it turns out this particular expectation gives something interesting already. I will show you, and it actually relates to the question, the properties of this product. And yeah, to understand the properties of this product, I need to explain a little bit about the social homology. And I get that most people understand this pretty well, but let me just quickly review. Suppose A is a social algebra. Then we have this partial chain complex. This the tensors of this algebra. And with the differential here, it's the partial differential. This is the piece component of the chain complex. And this partial differential, like, take for example, like tensors into like pairwise collisions. So for example, if you apply this partial to m plus p plus 1 tensors, let's call this one A1, A2, A central. You multiply the first two and then subtract the next two and so on. So it's like A1, A2. Subtract like the A1 tensor, A2, A3. And etc. Until you get the last two. And then you multiply the last one to the front with some signs, alternating signs. And then you can show like this word 0 and defines the partial homology. And this in non-commutative geometry, this partial homology plays a role like non-commutative differential forms, for example. And the way that you call this one is the classical partial Rosenberg theorem. Let me quickly review. So here's a basic example. So let's take this polynomial ring, and that's going to be the most complicated ring in this talk. So, not most. There's going to be a combination. Then actually, for this polynomial ring, you can write down a natural map. This is the thing you learn in calculus. It's like 10 from this chain complex, like to differential forms by sending, for example, suppose you have a bunch of functions. They can send it to the way you build up differential forms, like F0, BF1, BF2, and etc. And now the classical partial Rosenberg theorem basically tells you like this map is actually it's a chain map from this Hochschild complex to the zero complex here, which is a quasi-isomorphism. In particular, if you compute the Hochschild homology of the polynomial, and it's going to be the like n forms in these variables. And that's why in general, like if you have a non-commutative ring, I mean, that will play the role of like differential forms in this non-commutative launch. Okay. Now I will try to explain to you like the property of this product with the help of this Hochschild homology, this chain complex. And you'll see this formula. One way to write this formula is the following. And it's a differential form, and so you can write this one as like sum of indexes, for example, at 0, derivative, and etc. Sum of all the indexes, and that's the formula in calculus. Now you observe that this formula, that the formula we play every day, is the ordinary product. You multiply functions together, right? Okay. Now, what happens if you replace this ordinary product by this topological quantum product? And that will explain the property of this product as well. So that's what I'm going to do next. So adding this randomness produce a quantization and some nice algebraic structure. So let's come back to this product. So let's again look at this classical phase space. And it's my polynomial ring. It's like a position momentum on this phase space. Now we know, like we study quantum mechanics, we know this ring has a canonical deformation quantization. You can deform this one quantize. To Y algebra, like say in these two variables. I'm going to do a polynomial version. So this is like with you can deform by a parameter h bar and deform the product by the model product. And this is like a Y algebra. That's a canonical quantization. You can play this. Now, let's try to write down a formula in terms of this topological quantum product. Now consider the following map. Let's call this one rho h bar. At the vector space, it stands the tensors of this ring. Let me write in such a way. Actually, to this Y algebra. Let me probably let me write polynomial ring. By replacing this ordinary product by this quantum product defined by F0. Fm, my definition. The same formula, but by this quantum product. F0 plus I1, F1, and etc. Sorry, this should be differential forms. And then you have the dx1 and etc. If they do this naive replacement, got a map at the vector space. Now let me try to explain this property of this this quantum topological quantum product by this algebraic relations.
It's not clear that it's actually polynomial in each block, right? But you have to
You can show it is polynomial in each block, yeah. Yeah, because you can compute this one, for example, using some Simon diagrams, then it's going to be the vertex is polynomial, and the sum of diagrams is going to be finite and going to be polynomial in H bar. You can take some completion and so on, but this case is going to be polynomial in H bar.
So what does the order depend on?
Which one? Which order?
Which is the order of the polynomial? Does that depend on the number of f's?
The order of polynomial depends on the way you integrate on the circle. You insert these positions on some particular point on the circle, and to integrate. This is like a component of the configured space on the circle with cyclic order.
Do you
You place points on the circle in a cyclic order. So
sorry,
you
the
integrate.
degree of the polynomial, I meant. So the degree of.
Oh, you mean the order of the H bar? Oh, yes, depends on yes, the largest degree in H bar is the sum of the degrees of this polynomial. Yes. You can work with like formal power field ring or some other rings. You probably have to work with like a formal completion as well.
So that expectation value, that some differential form on cyclic insertions of the circle, right? Once you
Oh, evaluate as a function, like a function of x and p. This is like this is as a function.
but you calculate that thing and then you integrate over the t's, right?
Integrate over t, so it's end up with functions of x and p.
But given the f's, you got a differential form on cyc S1.
So this the value in this it's a ring. No, here there's no differential form here, but here I take the constant correlation for this particular functions, and then the integration form here. So this definition means value as a function. It is clear. For this definition, it is valued at an element of the polynomial ring with the H bar dependence.
The expectation value depends on Ti from Tm, so you've already integrated out, so it's not a form. The formula for that quantized product integrates that limit, which is a function of T1 through Tm, it integrates it over the cyclic configuration space. So it's no longer a form.
It's a function. Yeah. Or integrate all t's. Then everything goes over. And it only depends on x and p and H bar. And then if you try to extend this map, H bar linearly, and to this Y algebra, then you can get let me say this Alpha theorem here. This map integrates and the Hotter chain complex of the Weyl algebra to differential forms with H bar dependent, but it turning the Hotter differential. It's a Hotter differential for this Weyl algebra. The chain complex interturns this differential with the H bar BV operator. So here is this operator is the lead derivative with respect to the Poisson bivector of the canonical phase space. And this is a finite dimensional BV algebra. So basically, when you do this randomness, you generate this BV operator on this space. And the left-hand side, this algebraic structure is implemented by this Hotter chain complex. And you observe like there's a cyclic symmetry here, like rotation symmetry. And there's an operator like relating this cyclic symmetry. It's about this Coulomb operator. I didn't explain this one, but this is like about a cyclic symmetry. The interturns this Coulomb operator with the Durand differential. Yeah. And that's it. So this is a chain map, basically, which explains the algebraic property of this product. And actually, this is a quadratic model. So it can be viewed as like a quantum HKR map. So when you rescale H bar goes to 0, it becomes the classical HKR. So the analog of like a quantum HKR. Just because like it is classical limit, this quantum product reduced to the ordinary product, and that's the formula for the HKR. And finally, there's some properties like let me just mention as a remark. You observe like this is a BV algebra. When you have something like a BV, you can do BV integration. And if you compose this quantum HBR with BV integrations, you'll discover the Bayesian-Felder Schottky trait formula. Or this Hotter homology of this Y algebra. And I only explained the simplest case when this phase space is like R to N. But actually, you can glue this construction on the symplectic manifolds. If you glue on the symplectic manifold, and you can use this map to design some models like analog of this equivalent F1 equivalent localization formula. Get index formula. It's like algebraic index theorem. As originally formulated by like Karasov and Nessigan. Yeah, this process is like what is found in my period work, Brady and Jin Lee, and also Zheng Pinghui and Kai Xu. And actually, the way you prove this theorem basically is to show that this correlation, this definition, reduced to a formula explained in my favorite work with Zheng Pinghui and Kai Xu. And this is the algebraic structures which was somehow designed in this work as a model, but it is basically an HSZ model. And actually, you can do something more fun. So I probably won't have time to explain this the whole story. You can put this one on the torus. And this story is topological because it's topological limit. But actually, you can put on the torus and do some non-topological series. You can do some higher series. You can do some higher CFT. And in my work with jumping quick, we show like a similar construction into some higher elliptic placement. And a higher version of this algebraic index in the story. And this quantization process, basically, all this quantum information is generated by this randomness. That's expected. And this topological sector is by taking this large variance limit. And that's the relationship. I think I will stop here. Thank you.
So I have the following question. So you very elegantly expressed this deformed product in terms of the limit of the linear integral. But you also mentioned there is some diagrammatic expansion. Kind of, since you anyway send sigma to infinity,
Yes.
is there some other alternative combinatorial formula for the deformed product which would not be using sigma directly for the limit?
Yes. The precise formula for computing this limit is by inverting this D as propagator, and this is the vertex, and write down these Feynman diagrams, and that is the answer for this limit.
So you're saying that their sigma would be infinity from the beginning, and you will be choosing some Green's function for the d over dt on the line, right? Or on the line.
Yeah. So this is like a large volume limit on the line on the circle that you can remove this dependence at the last. Yeah.
But for your proofs, which presentation is better? This direct presentation in diagrams or the linear integral?
Oh, well, each one has its own nice property. For example, for computational reasons, like this Feynman diagram is much more direct. But if actually for this Vienna process, it's the thing I like about best. It's like the way you glue things is always purely non-perturbative, and you don't need to do this. For the calculation at the end, you find this perturbation answer, but the thing itself is not. And you can also try to do some higher dimensional versions for this kind of non-perturbative version of this quantization.
And the last question for me, if sigma is not infinite, does the product have some good properties, or if you don't take a limit, this guy is not?
Great question. The answer is I don't know. We haven't figured out precisely we're getting some more complicated correction terms. We don't have a good hands on this. But it's a great question.
So you change this PVX to something else, like can you say what comes out? You get another delta or something?
Oh, I don't know. That's probably the first model I tried. Yeah. So the reason for taking this PDX, I mentioned like this is topological quantum mechanical model, and it's also related to the AKSZ construction, and also related to some study in this condensed matter, which is called a strong magnetic limit. You consider some charged particles on the plane with the magnetic field turned on, the strong limits get this topological phase, and that's the same action. So there are different ways to explain why somehow we need this term. But you can do some other field theory, inserting some other action functionals here. And it gets something interesting, but probably not topological, I would say this. This is a nice topological model. And you see, like, you can imagine, like, yeah, I don't know the general situation, but this is, yeah.
So I was wondering, so if you're talking about one-dimensional field theories, then it's not surprising that, yeah, there's a connection there with the Wiener measure. When you're going to like the third point in your remarks there, you're talking about two-dimensional field theories, right? And so that part does not relate to any measure, right?
Yeah, oh, I haven't figured out the precise construction in the parallel way of this one. In probability theory, there's a word called the Gaussian free field construction, but it's not precisely leading to this index here. So the answer for your question is like, I don't know.
Can we extend this quantum product to some nice subclass of smooth function instead of
Probably, yeah, some microlocal stuff. And I haven't thought much about it. I would imagine yes.
Right, let's thank the speaker again. Reach the next one.